Good morning, ladies and gentlemen. Good morning, Professor CHOI. Very nice to meet you here. Today, in the morning, our planned lecture will be given by the Professor Mansoo CHOI from the Korea. I will introduce the Professor CHOI in a quick and a briefly introduction. The Professor CHOI obtained the BS and the master degree at the National University of Korea and obtained the PhD degree at the University of California, Berkeley in 1987, and Professor CHOI got the AARA Fellow Award 2007 and has been the IARA President. And Professor CHOI now is leading a frontier research group in the Nanoprinting technology applied on the solar cell, fuel cell, energy research field. And today, Professor CHOI will give us a very important topic relating to three-dimensional nanoprinting via charge aerosols. Please join me. Welcome, Professor CHOI.
Thank you very much, Chairman, for a nice introduction. I want to share my presentation file. Yeah. I'm very happy and honored to be here to give a presentation here at AAC 2022. And also I'm happy to see Professor Heinz Fisan here. And this morning I'm going to talk about our development of a new three-dimensional nanoprinting technique for the fabrication of three-dimensional nanostructures. Let me first briefly discuss about why we need three-dimensional nanostructures. In nature, 3D nanostructure can be found in photosynthesis system. Inside the plant leaf, 10 nanometer scale chlorophyll is assembled to form three-dimensional structure as you see from this AFM image. When photon is absorbed by chromophore, exciton is generated, and it is known that exciton energy can be transferred to neighboring chromophore without loss through these three-dimensional nanostructures. This means that the three-dimensional nanostructures exist for efficient physical operation in nature. Plasmonic solar cell is another good example showing the importance of three-dimensional nanostructures. Plasmonic solar cell utilizes metal nanoparticle array that enables physically thin but optically thick cells to maximize light trapping. Through this array of metal nanoparticles, light can be trapped inside the thin film solar cell. Therefore, path length of the light can be greatly increased and power conversion efficiency can be significantly improved. Surface enhanced Raman scattering source is a powerful tool to detect molecules very accurately, even at single molecular level, by exploiting the great field enhancement from these metal nanostructures. Depending on how you arrange these metal nanostructures, you can increase Raman signal significantly. Currently, much effort has been paid to develop three-dimensional nanoelectronics that could replace conventional two-dimensional semiconductors. In this 3D nanoelectronics, we need nanometer or micrometer scale metallic electrode. And also, this view graph will show 3D nano interconnections for the array of micro LED. Here, these blue dots are all LED. So we need to have an electrode to connect each micro LED like this. So we need this kind of a three-dimensional, electrode. Metamaterial is the material that could have a unique property that is not found in nature. Through this three-dimensional nanostructure, you can design very thin micrometer scale flat metal lenses that overcome the limitation of conventional bulky optic lenses, such as low numerical aperture. From these several examples that I just showed you, we realized that three-dimensional nanostructure could become a platform for novel nano devices. The next question is how we can manufacture three-dimensional nanostructures. Of course, layer by layer, conventional 3D printing can manufacture versatile kinds of 3D structures made of polymer, metal, or biomaterials. However, its resolution is at most 10 micrometers. That means conventional 3D printing cannot manufacture three-dimensional nanostructures. Electron beam lithography and focused ion beam lithography can be used to manufacture versatile 3D nanostructures, but as you know, this process rely on serial process. They need high vacuum. That means it is very difficult to scale up for mass production. Two-photon polymerization uses two-photon absorption process to generate a few hundred nanometer scale 3D nanostructures, particularly from polymers. However, they need specific photosensitive dye and post-processing. Therefore, it has this advantage of low throughput and low purity, particularly for metallic structure. Focused electron beam induced deposition use electron beam in vacuum to dissociate metal organic precursor for fabrication of few 10 nanometer scale three-dimensional structure. However, it has disadvantages: low throughput, since this is serial process, low purity, and high cost due to the need of high vacuum process. Capillary force can be effectively utilized to introduce nanoparticle into pre-patterned area to make this kind of nanoparticle patterns. If you want to make first pre-pattern, then you can easily make nanoparticle patterns. Or nanoparticles trapped inside this pre-patterned area can be used as a step to transport this nanoparticle onto this flat substrate. It's similar to gravure printing. Krauss et al. Used this concept to fabricate these lines and dots, nanoscale lines and dots consisting of nanoparticles. However, it seems to be very difficult to generating three-dimensional nanostructures from this method. In our aerosol field, Stephen Gersick utilized aerodynamic lens to focus aerosol and deposit to make this kind of structure. However, as you see, its scale is few hundred micrometers. That means we need to develop cost-effective high-throughput 3D nanoprinting technique, which enables multi-scale, multi-dimensional assembly in a parallel fashion under atmospheric condition with nanoscale resolution on large surface area, which should be independent of substrate materials. Let me tell you about our method, which we call electric field assisted aerosol lithography, EAAL. In our method, we use charged aerosol nanoparticles that are precisely positioned on the desired location via focusing electrostatic field. This is a parallel atmospheric process with a nanoscale resolution on large surface area. When we are dealing with nanoparticles in atmospheric condition, you need to be very careful about Brownian motion, since random Brownian motion is proportional to square root of diffusion coefficient of nanoparticles. And as we all know, if the particle size becomes smaller, this diffusion coefficient will become larger. For example, 1 micron particle move 7 micrometer due to Brownian motion in normal condition in 1 second. Even 10 nanometer could move more than 300 micrometer. But in order to make a 3-dimensional nanostructure, you have to manipulate your nanoparticles within nanometer scale resolution. That means we have to suppress this Brownian motion. So in our method, we use electrostatic force to suppress random Brownian particle deposition. So this is schematic our method. We inject ions and the same polarity charged aerosols into a chamber where electric field is applied. For example, positive ion and positive aerosols, you apply -4 kilovolts, and positive ion, positive aerosol should move toward substrate. Here in this chamber, we already put photoresist pre-patterned silicon substrate. Here, blue color means dielectric photoresist, such as PMMA. But as you know, the ion should have much larger mobility than charged aerosol. That means under the given electric field, ions should have much larger velocity than charged aerosols. That means ions first arrive on the surface of the pre-patterned photoresist pre-patterned silicon substrate before charged aerosols are approaching. That means now ions should be accumulate on the dielectric surface of the PMMA photoresist before charged aerosols are approaching. And then accumulation of ions will modify originally almost flat equipotential plane into convex shaped equipotential plane. Since charged particle should move in a direction perpendicular to the equipotential surface, this charged particle should be focused. It's like optical lens that can focus light. Our ion-induced electrostatic lens can focus charged material. So that means charged aerosol should be deposited only at the center of the opening area. So if we eliminate this photoresist, then you can obtain well-ordered nanoparticle patterns. This is our original experimental setup, very early time. So we generated silver nanoparticles using tube furnace, pass-through neutralizer and nano DMA, select singly charged monodispersed silver nanoparticles. In our experiment, we selected around 10 nanometer singly charged silver nanoparticles. We inject same polarity positive nitrogen ion together into a electrostatic precipitated chamber where we put photoresist pre-patterned silicon substrate. And this is the experimental result. you see there is no particle deposition on the surface of the photoresistor. Particles are only deposited at the center of the opening area due to the generation of the electrostatic lens caused by ion accumulation. You see 75 nanometer, but I want to emphasize that 75 nanometer is not a single particle, but multiple deposition of 10 nanometer silver particles. And if you eliminate photoresistor, then you obtain well-aligned, nanometer scale nanoparticle patterns. This focusing phenomena was previously observed by Fissang group in 2002 when sufficient amount of charged nanoparticles were deposited on photoresist surface. Here you see this is photoresist opening area. Due to the deposition of the charged particle deposition, there's some focusing effect. There's no particle near this photoresist layer. And they introduced electrostatic lens concept to explain the observed focusing effect. And in 1962, the focusing of charged material was also observed when electrospray deposition of radium and plutonium materials was done on Teflon mask after sufficient amount of charged materials were deposited on Teflon mask surface. But in our method, we use ions, not charged particles, to generate nanoscopic electrostatic lens. So if we do not inject ion, particles deposit everywhere. Of course, since charged particles deposit on the surface of photoresist near the interface between photoresist and opening area, there may be some reason for focusing, but anyhow, particles deposit everywhere. And this is a simulation. Horizontal line is electrostatic, equipotential line, vertical line, electric field line. Near the pre-pattern, you see a little bit focusing due to the existence of these charged particles. But we inject ion, so ion accumulation on this photoresist layer, that will modify almost flat equipotential plane into convex shaped equipotential plane. Electric field should be in a direction perpendicular to the equipotential plane, and then charged aerosols should follow this electric field line and deposit only at the center of the opening area. Of course, if you increase ion flow rate, you can control the focusing extent. 0 LPM particle deposit everywhere, 3 LPM particles are confined within 100 nanometer. You can see several particles deposit on the surface of PR, 4 LPM, 75, 6 LPM, 35 nanometer. Again, 35 nanometer is not a single particle, but multiple deposition of 10 nanometer silver particles. Of course, we can simulate this electrodynamic focusing of charged aerosols by solving Langevin equation, considering fluid direct force, Brownian random force, electric force, van der Waals force. Without ion injection, there is no focusing lens, so particle deposit randomly due to Brownian motion. But when you increase ion flow rate, 3 LPM, now particles charged aerosols tend to be confined within some region. 6 LPM case, initially random movement, but when these charged aerosols are approaching near the surface, they feel the existence of the electrostatic lens, and they are focused to deposit only at the center region. Of course, you can use electrospray of nanoparticle suspension to generate charged aerosols, but you have to be very careful, since when you use electrospray of charged nanoparticle suspension, usually you generate charged aerosol with excessive charge. Then if you apply electric field, the particle velocity, even though 10 nanometer, or few nanometer particles, particle velocity should be excessively high, and they could not follow focusing electrostatic field. So in this case, we used neutralized chamber first to lower particle charge, and then we successfully pattern nanometer scale, line pattern or dot pattern. Even protein can be patterned, or protein nanoarray having 50 nanometer scale, or you can introduce collagen protein within microfluidic channel using our method. Up to this point, we show that we need photoresist pre-pattern. PR acts as a generating tool for nanoscopic electrostatic lens. But can we eliminate this process? Can we eliminate this photoresist pre-patterning? In 2010, we developed a nanoparticle focusing mask. Now we don't have any photoresist pre-pattern, just a flat substrate. Just we place here mask, dielectric mask. This is non-metallic mask, silicon nitride mask having holes. And you inject ions and positive aerosols. As I already told you, ions should be accumulated first before target aerosols are approaching. This accumulation of ion generate this focusing lens, and particles follow this electric field line and deposit only at the center region, and then you remove mask. Then you generate these nanoparticle patterns. These are the nanoparticle focusing masks that we designed. This 500 meter square pattern, 4 micrometer line pattern. This is a few 10 micrometer epoxy mask. As one example, I show you 4 micrometer opening line pattern. As we increase ion flow rate, you can focus this charged aerosol up to 150 nanometer at atmospheric condition. Of course, this mask concept is very useful since you can translate after one deposition, and you translate and another deposition is possible. It's a sequential deposition, then you can increase density of nanoparticle patterns on the same substrate. And this focusing mask concept is found to be applied also on thick glass or on a flexible PET film. The next task was to develop the technique for 3D assembly of nanoparticles. So we used the same technique here. Initially, particles deposit only at the center surface area, but prolonged deposition will grow particles upward, maintaining width. But after this structure grow beyond the PR height, they interact with other structures. They grow both vertically and laterally. We presented this thing in 2008 AAA conference. 4 minutes, particle only deposit at the center region, 10 minutes, they grow upward, 40 minutes, now they grow beyond the PR height, 90 minutes, they interact with other structure and to become this kind of a 3D-dimensional nanostructures. Depending on, PR pattern, you can make this exotic shape of 3D-dimensional nanoparticle structure. Remember, each structure is consisting of more than few thousand of nanoparticles. We assemble each building block. This simulation here, initially they grow, but after they grow beyond this PR height, they grow upward and lateral direction, both direction, and finally we can make this kind of a 3D-dimensional nanostructure, which is similar to nano tree. Depending on the PR shape, you can make real nanoscale column, diameter 35 nanometer, height 220 nanometer, even this very, very small column consists of 1,000 of small nanoparticles, very compact structure. It's a four-leaf clover-like 3D nanostructure array of nanoparticles. As I told you, our process is a parallel process. We can, produce many three-dimensional structure at the same time. If you place two opening very close, each structure grow initially vertically, but after they grow beyond the PRI, they tend to be connected to generate this micro table-like structure. Okay. Or if you place four opening very close, then you can generate this beautiful nano flower having a central hole. This is also simulation. Initially, they grow from each opening, but after they grow beyond the PRI, they tend to be connected and to make finally the micro table-like structure. Then our question was, if we make another hole between two holes, what happened? Of course, initially, each structure grow from the opening, three structures. But the structure that grow from the central hole, after they grow beyond the PRI, should have two different directions for growth. The split direction we call bifurcation assembly of charged aerosols. So this structure can be split into two different directions. This is also okay. And next question is, if we place one hole at the center among these three holes consisting equilateral triangle, then the structure that grows from the central hole should have three different directions, split into three different directions. Okay, and then finally they are all connected. It's like a floating bridge, like a three-dimensional structure. Or tetrafurcation, pentafurcation, or hexafurcation. And we tried to apply this, bridge-like structure for gas sensor. So we made tetrafurcation assembly 3D structure for 3D gas sensor. Here, this is floated, multi-directional bridge structure. Compared to conventional thin film gas sensor, our 3D gas sensor show much higher sensitivity, more than twice. Repeatability and durability. Also, we applied our 3D structure for surface enhanced Raman spectroscopy substrate, since we can make different kinds of 3D structures. 4-petal flower structure, this is 6-petal flower structure, 8-petal flower structure, and after depositing gold layer, we can measure Raman spectrum, conventional particle film, black. As we increase petal number, you see Raman signal is significantly enhanced. And electromagnetic simulation revealed that the hotspot exists between these petals. That's the reason why we have higher Raman signal for higher number of the petal, flower structure. We also measure dark field scattering from this, multi-petal flower structure, and you observe different colors, blue color, orange color, red color. That means our three-dimensional flower structure could have multiple plasmon resonances. Then at the time we try to utilize these multiple plasmon resonances for the solar cell, since plasmonic solar cell use trapping of photons at a certain wavelengths that is similar to, plasmon resonance, but our structure can, reveal multiple resonance. That means we could make plasmonic solar cell that can trap photons having wide spectrum. So here, first we made this three-dimensional structure, and then by deposition of the silver, we made the 3D back reflector, and from this we made nanocrystalline silicon thin film solar cell with collaboration with Dr. Jun-Sik Jo in Korean Institute of Energy Research. In order to make solar cell, we have to scale up our three-dimensional, nanostructure fabrication, okay, at least few centimeter scale. So we developed 2014 multi-tip spark discharge, and then we can pattern three-dimensional nanostructure large scale 5 centimeter, 5 centimeter. And from this sample, we can now synthesize silicon solar cell. This is our silicon solar cell applied with our 3D, nano structures. Of course, we also observed multiple plasmon resonances, several peaks. And as you see, external quantum efficiency is increasing compared to flat conventional solar cell, in wide spectrum, range. We believe this is due to the existence of multiple plasmonic resonance from our multi-petal, three-dimensional nanostructures. And of course, performance and efficiency is significantly enhanced compared to flat solar cell. We also applied our 3D structures for perovskite solar cell. Perovskite solar cell use, TiO2 nanostructures as an electron transport layer, but they just spin coat, flat TiO2 layer. But we know how to make pattern of the TiO2 layer. So first we make this flower structure, and then we can replicate PDMS mold. This is PDMS mold. And using this PDMS mold, we can make patterns of a major porous TiO2 layer like this. We want to enhance light scattering using this kind of a three-dimensional pattern. And then external quantum efficiency, our case, 3D patterns, external quantum efficiency is increased, and power conversion efficiency also increased due to the existence of a three-dimensional structured TiO2 layer. Success of 3D assembly of nanoparticles is strongly dependent on the building block, nanoparticle. It is natural, obvious, small building requires small building block. For example, 35 nanometer diameter 3D column needs particles less than 5 nanometer. We cannot make 35 nanometer 3D column with 10 nanometer particle or 20 nanometer, too big. And agglomerate particle cannot make a dense structure. Of course, depending on your application, you may prefer to use agglomerate particle, for example, some catalytic, application. But if you want to make a dense nano building, then you need to generate few nanometer unagglomerate nanoparticle at sufficiently high concentration. To achieve this, we developed new spark discharge generator. This is pin-to-plate spark discharge. Conventional spark discharge use rod to rod, but this pin-to-plate discharge spark generator allows very, very quick quenching to stop to stop agglomeration. And from this generator, we can obtain unagglomerated nanoparticles compared to this rod to rod. However, we found some problem for our pinto plate spark discharge chamber. Although this pinto plate type generate unagglomerated nanoparticles, very, very small particles. However, we found that size distribution is changing after long time operation. This is initial 0 hour, but 12 hour, now we are generating much smaller. Okay, so that inconsistent for long time operation since the erosion of this tip and this plate. Then we developed again new type wire in hole type spark discharge. This thin wire cylindrical hole. And in this case, we found that size distribution is relatively similar even after 12 hours. At the same time, we can generate unagglomerated nanoparticles. This electrode erosion shape tip and pin to plate type, you see this erosion of the tip will change size distribution after long time deposition occurs. But in our wire in hole type, relatively uniform size distribution we obtain. And later we found more practical spark discharge generator. That is wire to cylinder, very thin wire, and this is very thin hollow cylinder. Okay, this is very simple. And if we use this wire to cylinder type, we can generate unagglomerated nanoparticles, and time stability is very good, long time stability, relatively uniform. So actually, the development of this wire to cylinder type spark discharge was very critical for our success in developing three-dimensional nano printing via charged aerosols. Now, this is my last topic for this presentation. Now, I already told you we can use mask, focusing mask, but at the time, this mask is just attached on the substrate. Now we float this mask from the substrate. That means we separate between, this mask and substrate. Then we can move mask or substrate freely while we are depositing nanoparticles. Okay? In that way, we can design our three-dimensional structure. Of course, even we float this dielectric silicon nitride mask, ion deposition on this mask surface will generate this electrostatic lens, and electric field is focused. Charged particle just to follow this electric field, and then this substrate is moved in 3D dimension using 3D piezo nanostage to make versatile kind of 3D-dimensional nanostructures as you wish. So this might be regarded as a real 3D nanoprinting technique using aerosol technology. Okay, so we can move this substrate in G direction, lower substrate. Initially 5 minutes, this starts 10 minutes, they grow 25 minutes, very high aspect ratio, nanowire shape, since we move substrate. So this aspect ratio is 36, diameter 300 nanometer. We used the 4 micrometer hole. So this electrostatic lens will generate 300 nanometer, diameter wire, very, very long, high aspect ratio, wire. While you make this high aspect ratio wire, you can change material using 4 different, spark discharge, wire to cylinder type, the advantage of wire to cylinder type spark discharge can replace your wire and cylinder easily. So if you change AG, copper, gold, palladium, you can change. So initially you deposit palladium first, and then gold, copper, silver. So multi-material can be deposited on a single three-dimensional structure. Or you can also deposit alloy or any other type. You can just change this source. Also, after you deposit one structure, you move stage, and then you can deposit again. So one step will generate around 3,000 nanostructures at the same time. If you repeat 8 times, you can make more than 20,000 nanostructures per millimeter square. So this is parallel process. We can increase density of the 3D nanostructures on the same substrate, or you can change material. Okay, on the same substrate, you can make a different material, three-dimensional nanostructures. You can also control the voxel width. Control parameters. You can change distance between mask and substrate. Okay, mask and substrate, or you can change mask hole size from 4 micrometer to 2 micrometer. You can change ion flow rate to increase focusing capability. So now you see 95 nanometer, sub 100 nanometer scale, pillar using 2 micrometer hole mask pattern under atmospheric condition. Or you can design different shape of the mask to fabricate different shape of three-dimensional nanostructure, very, very compact structure, since we generate unagglomerate nanoparticles. Now, while you deposit nanoparticles, you can move mask or substrate in X direction. Okay, and then electric field line can be changed. Then you can make a slanted structure. Okay, vertical pillar. Now, if you move this mask in this direction, now you can make 30-degree slanted structure, 45-degree, or even 90-degree, even downward growth. Okay, you see, this field is like this. The nanoparticle should follow this field line, and downward growth could become possible. Okay, and this is simulation. Also, initially grow vertically, and then if this mask is moving, the slanted structure, depending on this stage velocity, you can control angle of the slanted structure. Or now you can move substrate like circular motion, XYZ, okay, downward, but making circular motion. This is 180. You see, this is a half circle. This is helical structure. Or 360, you can generate helical structure. Or zigzag, or 70-20, 2 turns, 1 turn in clockwise, 1 turn counterclockwise. As you wish, you can control. And also, this process can be modeled. Dr. Peter Pihita, who worked in our group, developed this modeling by solving this electric field line. Our technique is relying on electric field line. Electric field line is a drawing tool in our technique. So if you change shape of the electric field line, then you can change your structure. And then we compared our modeling with experimental result. They show very good agreement. And this modeling can be used as a very nice tool to optimize our 3D printing methodology to make the desired shape of the three-dimensional structure. Okay, and our technique actually has two different modes. Tip-directed growth mode I just showed you, like this, particle deposit on the top of the growing structure. But if you move this mask too fast, and then particles do not deposit on the top of the growing structure, they deposit just on the surface. This is the surface riding mode. Of course, focusing is existing, but still, for the fast moving case will result in surface riding. Surface riding mode, this is a tip growth mode, but if you move stage very fast, 25 nanometer per sec, now particles do not deposit on the top of the growth and top of the structure, they deposit on the surface of the substrate. Using this riding mode, this is function like riding a pen, like a ring structure, some letter structure. So our technique has two different modes, tip-directed growth mode and riding mode. And we combine this. First, we make tip-directed pillar, and then riding mode make this horizontal line, and tip growth mode make this pillar and 90-degree slanted pillar. Then we can generate this kind of a vertical split ring resonator. And Professor Jun Song-lo, we worked together, simulated structure and showing magnetic resonance. And Lee Ken, Dr. Nanata and Dr. Chai measured the reflections, and they proved that our structure show magnetic resonance near 19 micrometer. So that means our technique is enabling to manufacture the metamaterial. Okay, just I want to show this here, vertical split ring resonator in atmospheric condition. Okay, finally, I want to summarize my talk. We developed 3D nanoprinting technology based on aerosols, which we call electric field assisted aerosol lithography. And we demonstrate our techniques of fundamental nanofabrication methodology that could be applied to different kinds of 3D nano sensors or metamaterials or solar cells. Our 3D nanoprinting technique is a fully dry method without needing polymer or inks, and produce thousands of 3D nanostructures at the same time, meaning this is a parallel process with a multi-material capacity at the nanoscale resolution under atmospheric conditions. Finally, and greatly, I want to acknowledge great contributions made by my many doctoral students and researchers who work with me and collaborators. And finally, I want to acknowledge, contribution made by sponsors. Thank you very much for your attention.
Thank you for the Professor Choi's very insightful and a very important lecture. Thank you very much. And then we will have time for the Q&A. Please, any question? Professor Xiang.
Hi, Professor Choi. This is Tachi from Taiwan, National Taiwan University, NTU. And thanks for the great talk and using. I think the most important what I get is electrostatic focusing method applied to building the 3D structure. Initially, there is an aerodynamic lens. You talk about that. So my question is more like first, how to get how many charge you put on the aerosols, and how to let the particle get charged stably. And second, those structure actually is more like a aggregate, and I guess it's still under low pressure condition. And how strong is the structure? Since the put together is solely based on van der Waals force. So is there any limitation to like for their structured length or aspect ratio, etc.? And that is two of my questions. And yeah, thanks. Thanks for a great talk.
Okay, I want to answer your second question first. Of course, the structure, nanostructures, are I mean, withstanding with the van der Waals force, but you can enhance the strength by using this electron beam irradiation. After you make nanostructure, and electron beam irradiation will sinter a little bit to make a stronger. So even after sonication, we can, I mean, these structures survive. Without this sintering, sonication will, eliminate all the particles. So depending on your application, if you need application needing stronger structure, then you have to use this kind of post-processing. And actually, first question, actually, I couldn't understand. If you ask once more for the first question.
The first question is, I just curious because those particles are get charged, supposedly should be charge aerosols. So how many charge you have on each particles, and how do you do that stable?
Okay. I mean, if when we use spark discharge, then the charge fraction may be very small. Okay. But anyhow, neutral particle cannot be attracted through electric field. They do not contribute. Even though small fraction is generated as a charged aerosols, we are utilizing that. And if we use electrospray, then I think most aerosols are charged aerosols. And if you select nano DMA, then the most aerosols are singly charged nanoparticles.
Okay. Yeah. Thanks for the response, and thanks. And I think there is one question from online, right?
Yes. Professor Choi, can you see the question right on the screen?
Okay, Chang-Fu Wu. Okay, with regard to the nanocells for detecting collision, do they generally have sufficient MDL for ambient monitoring? Sorry, actually, I do not understand about MDL. Sorry.
Okay.
Yes, I'm not the specialist on sensors. So if you send me email about the detailed explanation of your question, then I will answer through email. Okay.
Okay. Thank you. Okay. This question will be answered by the email. Okay. And yeah, this is an MDL issue. Okay. I know. MDL, the method detection.
Method detection limit.
Yeah. But I know. But this question will be answered by the email. So because Professor Choi said that this not just directly related to the MDL. Sorry. Any question, Professor Chen, about the mask? Okay. Mas.
Okay, good morning, Professor Choi.
Yeah, good morning.
This is C.C. Chen of National Taiwan University. Thanks for the fascinating talk. I can feel the excitement and the fun you have in the lab. Well, my question is in line with T.C. Xiao, but I think you already answered that for this small particle, it's difficult to charge them, right? But I just like to know is there any? I mean, your design, are there commercialized or the more of the future application? I know that they will improve the solar cells capture efficiency, but any other applications?
Yeah, I think this technology is a fundamental manufacturing technology, particularly for nanostructure, manufacture. So the application should be very diverse. Okay? But still, we have to solve certain problem like large scale, area. Scale up of our printing, 3D nano printing technology is needed for the real application and real commercialization. And also, of course, we focused on making very, very small, 3D structures. But at the same time, we have to make medium size or larger size, okay? But our technique is more effective in generating very small nanostructures. So we have to find applications that need this kind of three-dimensional nanostructures. I think in future, industry utilizing 3D nano electronics and also 3D nano optics field, our technique could be utilized for practical manufacture of the devices. Since we do not need vacuum or this is parallel process, very practical way and very dry. So that means we ensure purity. So I think we have to see in the future for the commercialization.
Okay, thank you. I think I'll see you in Aden, right? Okay, thanks.
Thank you.
Yes, our time is almost over. Actually, it's a little bit over. Okay, and please join me. Thank you, Professor Choi, for his insight.
Thank you very much.
Thank you, Professor Choi. Thank you.
Other than that, Professor Chu, thank you so much for such an insightful information on the three-dimensional nanoparticle and nano printing. Thank you so much.
Thank
and
you.
also thank you. As a token of appreciation, our local community has made a plate for your speech today. And as you can see on my left-hand side, the local community has made this plate for you as appreciation. This plate is a miniatures of a very famous sculptures from the Zhumin Museum, and it's a symbol of Tai Chi. And I know that's also very important culture in South Korea. And we will ship this plate to you after the conference. Once again, please join me to thank our speaker today.
Thank you very much. Okay.
I want to invite our professor and our speaker online to take a group photo. So please, the professor here to join us for a group photo, and the people online, please turn on your computer screen for a group photo. I will make an announcement for 1, 2, 3. Then please give your best smile. 1, 2, 3. Okay, one more. 1, 2, 3. Good. Thank you very much.
Thank you very much.
Thank you.
Okay.
We will now
Okay.
take a, thank you. We will now take a brief coffee break. Please come back on time by 10:30 for the session for today. Thank you so much. Thank you.